welcome to Tiger Bytes Physics. Brought to you by the one and only Tiger Bytes Physics icon, the fabulous, magnificent, stupendous, all-knowing, all-seeing, Mr. ICAN. Hi there, I am the Tiger Bytes ICAN. I am here to help you master objectives for force and the laws of motion. Here are our objectives for force and the laws of motion. The list includes key math skills we will need to solve problems about force and motion. Pause the presentation. Read these, think about them for a moment, and then continue. Here is a physics problem that illustrates all of our key objectives. If you can understand and explain this problem and then set up and solve others like it, you will have mastered the key objectives. Once upon a time, there was a student, a box of books, a ramp, and a rope. Pause the presentation. Read the problem and set up your problem-solving checklist before proceeding. You will get more out of this presentation if you make the attempt prior to looking ahead. You must find the acceleration of the box up the ramp in meters per second squared. You know some key information. Correct your problem-solving checklist if it does not match this one and then proceed. Note that omega is the angle of the applied force on the rope with respect to the ramp. Theta is the angle of the ramp with the horizontal plane. Before we can solve the problem, we must visualize it. That almost always means we need to draw a diagram of the problem. Start by taking what we know and placing it on the diagram. Note that our original frame of reference uses a coordinate system where the x-axis is parallel to the horizontal plane and the y-axis is perpendicular to the x-axis and horizontal plane. Also note where we drew our angles for theta, the angle of the ramp, and omega, the angle of the applied force relative to the ramp. Pause the presentation, and draw this as your starting point. Make the diagram large. Use a whole sheet of paper. After all, Mr. ICAN has reminded you many times that paper is cheap. It is the tuition that is expensive. The applied force is a contact force because we must have contact between the rope and box for the force to affect the box's motion. We also know that gravity, a field force, is also being applied to the box. So, we should add the gravity vector to our diagram. Note that its direction is straight down along our original y-axis. Now let's change our frame of reference to a more convenient one for this problem. We will want our new x-axis to be parallel to the direction of the box's movement along the ramp. In other words, the new x-axis is the surface of the ramp. That would mean our new y-axis would be perpendicular to the ramp. This new frame of reference will make our problem much easier to solve. Now, we can see that our vector for the gravity force is no longer straight along the new y-axis. So, we will want to see if we can identify its components in terms of the new x and y-axis in our new frame of reference. We start by drawing the y component of the gravity force and label it F sub gy. It is in line with our new y-axis and perpendicular to the ramp. We should do the same with the x component of our gravity force. In this case, it has a direction parallel to the ramp. Since the gravity force would want to push the box down the ramp, the direction of F sub gx is down the ramp. Note that we now have a right triangle with the x and y components of gravity as legs and the original gravity force vector as the hypotenuse. We can now determine that the top angle of our new right triangle is equal to theta, which was our original angle of the ramp to the horizontal. How do we know this? Well, it is elementary geometry based upon complementary angles and the fact that all angles of a triangle sum to 180 degrees. Now we will turn our attention to the applied force. That is the force that the student is applying by pulling on the rope at an angle labeled as omega, which is relative to the direction of the ramp. That means that omega is also relative to our new x-axis. The x component of our applied force on the rope is what will actually pull the box up the ramp. It is labeled F sub ax. The y component of our applied force on the rope actually pulls up on the box as if it were trying to lift the box from the ramp. It is labeled F sub ay. Now we have two right triangles, but we are not finished with our diagram. First, we need to draw the vector for the normal force. It is the force exerted against the box by the ramp. It is always exerted at a right angle to the surface. Since we often refer to right angles in math as normal angles, we call the force the normal force, i.e., the force exerted at a right angle to the surface. Our final force for our diagram is the friction force. That is the contact force that is always in the opposite direction of the relative motion between two surfaces. In our case, we are trying to pull the box up the ramp, so our friction force is in the direction opposite that in which we are pulling. Now, this is our diagram that we will use to solve our problem. Pause the presentation and make sure your diagram is complete. If your diagram is sloppy and hard to read, throw it away and make a new one, and yes, keep thinking about that expensive tuition in your future. Now, let's pause and reflect on our objectives for a moment. So far, just by completing our problem-solving checklist and drawing our diagram, we have described how force affects the motion of an object, constructed and begun to interpret our free body diagram, explained the difference between a contact force and a field force, identified some everyday field and contact forces in our problem, and used math skills to diagram a vector problem and select an advantageous frame of reference. Mr. Ican says, great work. Now we can actually use what we have done to solve our problem and determine the acceleration of box up the ramp. Starting with our diagram, we will now isolate forces in the y and the x direction within our new and convenient frame of reference. If we look just at the forces in the y direction, we can see that we have three forces. They are the y component of the gravity force, the y component of the applied force, and the normal force. We know that the sum of these forces must be zero since the box is not accelerating up or down in the y direction. So, we know F sub gy minus F sub 8y minus F sub n equals 0. We start with F sub gy and subtract the other two because the normal force and the y component of the applied force are in the opposite direction of the y component of the gravity force. From this we can easily see then that the normal force, F sub n, is equal to F sub gy minus F sub 8y. We will need the normal force to solve for the friction force in the next step. We now isolate the forces in the x direction. We are pulling the box up the ramp with the x component of the applied force. At the same time, the x component of the gravity force and friction between the box and the surface of the ramp are working directly against our effort to move the box up the ramp. In this case, we must have an unbalanced force called the net force in our favor if we are to get the box to accelerate up the ramp. It should be evident from the diagram that our net force called F sub net should be equal to F sub ax minus F sub r minus F sub gx. We must also use the results of the previous step where we determined the value of the normal force. Since the coefficient of kinetic friction is defined as the ratio of the friction force to the normal force, we can determine that the friction force is equal to mu sub k times the normal force. Now we are almost ready to complete our problem-solving task. But first, let's pause on the next slide and reflect about key objectives. Mr. Ican is back and says you should focus for a moment on the highlighted text. Using your diagram, you can see that we have calculated the unbalanced force in the x direction and the equilibrium force or normal force in the y direction. We were using Newton's first law when we did that. We also used the concept of action-reaction pairs, especially when we look at how the normal force works. That is Newton's third law. Finally, while we did not directly calculate a coefficient of friction, we needed the definition of mu sub k to determine our friction force once we knew our normal force. We did all of this by simply interpreting the situation clearly depicted in our diagram. So let's get down to solving for the acceleration of the box up the ramp. Here are our two key equilibrium equations from our diagram. Before we go further, let's do a short trig review. We know the definition of sine, cosine, and tangent. In math class, we usually think in terms of x, y, and the hypotenuse. In physics, however, it is more useful to think in terms of opposite, adjacent, and hypotenuse for our angle theta. This is necessary because we altered our frame of reference to make this problem easier to solve. One of our triangles, the one associated with the gravity force, no longer matches the original idea of x and y for cosine and sine. However, we can use the idea of adjacent and opposite quite nicely for any triangle in our diagram. Okay. We can now use the idea of opposite and adjacent for our angle theta in the gravity force triangle and see that the y component f sub g y is equal to the hypotenuse f sub g times the cosine of theta, since the f sub g y vector is adjacent to the angle. At the same time, we see that the y component of the applied force F sub ay is equal to the applied force F sub a times the sine of omega, since F sub ay is opposite omega. Now we can simply solve for the normal force by substituting for F sub g y and F sub ay. We also are reminded that the force of gravity is simply expressed as an application of Newton's second law, i.e., force equals mass times acceleration. So F sub g equals mass times g, the acceleration due to gravity. Use g at positive 9.81 meters per second squared in this case because we altered our frame of reference and g is no longer straight down. We took the signs of our forces into account who we drew and interpreted our diagram. We now do some similar calculations for our net force equation. In this case we see that the x component of the gravity force is equal to F sub g times the sine of theta. The x component of the applied force is equal to F sub a times the cosine of omega. And we know that our friction force is equal to mu sub k times the normal force we determined on the previous slide. Hey look, it's Mr. Ican again. He wants to remind you that you have just covered a few more of the key objectives. Pause a moment and reflect. Now that you have calculated the net external force on the object, you are ready for the final step. Start with what we just determined the net force to be. We have enough information to calculate that force since we know mass, g, the applied force, and both angles. Using Newton's second law, we know that the net external force on the box is equal to its mass times its acceleration up the ramp. So if F equals ma, then we can easily solve for A by dividing the net force by the mass. The table on the right provides key inputs and results if you develop a spreadsheet to perform the necessary calculations for this example. Well, that's it. If you understand this problem and could explain it without referring to this presentation, you have a pretty good handle on the objectives for force and the laws of motion. A students will be able to explain it to others and set up and solve similar problems without referring to this example. B students will be able to set up and solve similar problems using this example as a reference. C students will be able to explain this problem without referring to the example. And the rest, well, you need to keep studying this example until you can at least master it to a C level. This is Mr. Ican saying so long and may the force be with you.